Right. Well, thank you very much, everyone, for joining us. Thank you in particular to Daniele, who agreed to step in at short notice and give a talk on something that I've been particularly intrigued by over the last year plus, his prediction contests, sophisticated prediction contests for major sporting events. And so I was really pleased with the World Cup taking place right now. And with the European football season about to begin, that Daniele was willing and able to fill in a gap in the schedule and talk about probabilistic prediction contests. Daniele, I will just simply let you take over from here and take away your talk. Are you happy to take questions as we go along?
Yes, actually, I would very much encourage questions, during the talk, and feel free to interrupt as a sort of regular econ seminar. So thank you very much, James, for hosting me. I should say, this is going to be a little bit of a unusual talk. It's not really a research paper. It's more a bit of an overview of some issues that could be interesting and sort of worth writing a paper about, but it takes bits and pieces from various literatures. I have to say, when I was preparing this talk, I figured out that probably a lot of the people in this audience are actually a lot more expert than I am on what I'm going to talk about, or at least on some of the topics. So this is going to be a little bit amateur hour, and I apologize for that in advance, but let's see how it goes. Okay, so as I said, questions welcome. Title of the talk is going to be Probabilistic Prediction Contests, or sophisticated, but probabilistic is a little bit more formal. And I'm going to start with something that is not about sports. This is the opening page of 538, which you may be familiar. It's sort of a website that was founded by Nate Silver. It was about data journalism. And this was their screenshot on the eve of the 2016 United States presidential election. Okay, and so, who will win the presidency? You had this figure, on whenever it was, November 4th, 5th, Nate Silver and 538 predicted that Hillary Clinton had a 71.4% chance of winning the election and Donald Trump a 28.6% chance of winning the election. And they had this nice map of the United States with, every state color-coded by, the chance that each one of the two candidates would win that particular state. Okay, and so I highlighted here Wisconsin, which is sort of a middle-ish blue. So Clinton was given an 83.5% chance of carrying with Wisconsin, Trump 16.5%. Okay, so Hillary Clinton was a big favorite, and as you probably know, that was not how the election turned out. Okay, so Donald Trump won, by the way, carrying Wisconsin and Michigan and Pennsylvania, these sort of middling blue states that were predicted to go pretty strongly for the Democrats. Okay, so was 538 wrong? Many pundits were shocked by the election results, and there was a lot of hand-wringing, and how could the polls be so wrong? How could we miss this, et cetera, et cetera. And Nate Silver spent the next several months arguing, or years arguing, 2 points. First of all, that events that have a roughly 30% probability of happening happen about 30% of the time. So if you ever played Monopoly and you need to get a 9 or higher to just, run past, Boardwalk or Mayfair, whatever it's called in your native country, that happens sometimes. Okay, sometimes you get lucky or sometimes you get unlucky, and it can happen. And the other claim that Nate Silver made is that 538's forecast was actually more accurate than many others. So it was less bullish about Clinton's chances than many other, expert forecasts. There is this Princeton professor who I thought was a political scientist, but he's actually a neuroscientist, Sam Wang, who was engaged in some sort of pretty heated argument with Nate Silver before the election, that he thought that Clinton would have a 98 to 99% chance of winning the election, and he promised that he would eat a bug on live TV if Trump won, which he ended up doing. And so if you look Sam Wang eating bug, you'll find the YouTube video somewhere online. So the question is, how do we know that 538 indeed produced a better forecast than the Princeton Election Consortium, which was this, website, run by Sam Wang and sort of other outcomes. So we want a way to evaluate these probabilistic forecasts. And why we want to do that? Because, in general, we want to know who makes sort of accurate probabilistic predictions. I don't think that this is, particularly new or original insight, that it's important to assess accurate probabilities. It is key to decision making in a variety of contexts. Okay, so what is the probability that Trump will be elected president in 2024? That could affect, maybe your investment strategy, or where you want to go and live, or whether you plan to move to the U.S. or whatever. You perhaps want to know what is the probability that the U.S. will enter a recession in the next 12 months. It's the end of June, and I know it's probably pretty hot in a bunch of places. So you may be curious about what is the probability that the average global temperature will rise by 0.5 degrees Celsius by 2050. In fact, this weather forecasts or meteorological forecasts, that's where a lot of this literature really started from. And of course, you can apply it also to sporting events. What is the probability that England will win the Women's World Cup? And I learned that they beat Denmark. Their chances must have gone up a little bit. Okay, I'll add that probabilistic forecasts are becoming increasingly common, in part due to 538, but not only. You see that in all sorts of places. This is the probability that some event will happen. Experts will emerge claiming that they can deliver the most accurate forecasts. So these can be political pundits, or mutual fund managers, or people who give advice about betting. And I added here as a footnote, this presentation does not endorse gambling. Be careful about gambling, but it does touch on some things that are sort of adjacent to gambling. So we'll talk about it. Okay, so what is a probabilistic prediction contest? Okay, so here's a little bit of formal definitions. So it's a contest, is a game with n players that they submit a probabilistic forecast, which I call F, for a series of m events. Okay, and F little m is itself a vector assigning probabilities to each one of k possible outcomes for event m. Okay, so for example, event m could be what is the outcome of the England-Denmark football game, and there are three possible outcomes. England wins, ends in a draw, Denmark wins. And then x is the vector of actual realization of events, and d is just a vector of dummy variable that takes on the value 1 if the outcome of event m was equal to k, and 0 otherwise. Okay, and so these are just sort of the basic ingredients of the model. And for a contest, we need a scoring rule. Okay, so we need a mapping that takes the forecasts F and the realization of the events D and transforms them into a number. Okay, so it's a mapping from FD onto the real line, and the winner of the contest is the player with the highest value of S or the lowest value of S. You can always multiply things by -1 given the actual realization of events. Okay, so here are some examples of what these events could be. Okay, so XM could be, in the political example, presidential candidate wins state M, and sorry, that's sort of one. The Democratic presidential candidate wins state M, or the Republican presidential candidate wins state M, and you have 50 states, and you have to submit a probabilistic forecast for each one of those 50 states, just like we saw in that opening slide. Okay, example number 2. What is it? How much will it rain in Boston in the next month? And for every day, I can say, well, there's a probability 0 that there will be, the event could be there's either 0 centimeters of rain, meaning it doesn't rain, or between 0 and 2, or more than 2, or you can transform any continuous variable into sort of a set of discrete bins. Okay, and in the example that I'm going to talk about more later is, the round at which England will be eliminated in the Women's World Cup. Okay, so these are all the possible outcomes of that event, XM. So England could be eliminated in the group stage. Actually, I think that's no longer possible. They could be eliminated in the round of 16. They could be eliminated in the quarterfinals, in the semifinals. They could be the losing finalist, or they could be the winner, meaning that that's also sort of a round of non-elimination. Okay, so let's talk a little bit about scoring rules. Here are some of the most popular ones, and there's a rich literature. By the way, at the end of the slides, I have sort of included a sort of bibliography with a lot of these sort of some of the articles that I cite in the slides, and some that are just sort of otherwise relevant. So one of the most common scoring rules is just a quadratic loss function. Sometimes it's called the Breyer scoring rule. So you basically, that's what you get. FM is your forecast. FMK is your, the probability that you assigned to to outcome K in event M. And DMK is, 1 if outcome K happened in event M and 0 otherwise. You take the difference, you square the difference, and you sum over all of your forecasts. Okay, so that's a very common one. An alternative is the log loss scoring rule. So it looks a little bit like a likelihood function. In this case, you want to actually maximize, the value of S. And the ranked probability scoring rule is a little bit like the Breyer scoring rule, but it's really looking at cumulative probabilities, like a CDFs, for different events. And this is, it makes sense in settings where the outcomes are ranked. Okay, so for example, does England, is England eliminated at the in the group stage, the round of 16, the quarterfinals, those are ranked events. So you can sort of think of, not just the PDF of being eliminated at each point, at each round, but the cumulative distribution of being eliminated at each round. Okay, it turns out that all of the aboves are example of strictly proper scoring rules. Okay, what is a strictly proper scoring rule is that if you as a forecaster wants to maximize your expected score, your optimal strategy is to issue the actual probabilities, if they are known, or whatever you think the probabilities are. Okay, and all of these, these 3 scoring rules, they have this property. One can think of other scoring rules that do not necessarily have this property. So how do you choose a scoring rule? It turns out that the choice is not completely innocuous. Okay, so here are 2 forecasts for England's stage of elimination at the World Cup. Okay, so both of these forecasts are pretty bullish about England's chances. It thinks that England has an 80% probability of winning the final. Okay, that's the WF. But forecast 2 is even more bullish. It says England will for sure at least reach the final. Then if it gets to the final, it wins the probability 0.8. But it may lose the final with probability 0.2, and forecast 1, is a little bit more uncertain about what will happen, once you get past the first round. Okay. All right, so tournament happens and England wins. I know there's a lot of English people in the audience, so I'm trying to get likes. All right, so I'm ranking the two forecasts, and I'm multiplying everything by -1, so lower scores win. And it turns out that, depending on which scoring rule you use, you can get, different winners. Okay, so the log score is interesting because what matters, if you look at the formula again, the only thing that matters is the event that actually took place. The value, the event K, the outcome K that actually took place. This, dummy variable takes on a value of 1. All the others are 0. Okay. So forecast 1 and forecast 2 are equally good, in case England wins, because they both assigned England 80% probability of winning the World Cup. Okay. The Breyer scoring rule actually prefers forecast 1, okay, to forecast 2. And the reason is that, the Breyer scoring rule takes into account also all of the, incorrect predictions, or, the events that didn't take place. And, because you're squaring the forecast error, this 0.2 error for forecast 2 gets a lot of weight. Okay, so Breyer ends up doing less well than forecast 2 ends up doing less well than forecast 1 if you use the Breyer scoring rule. But the opposite is true if you use the rank probability scoring. Okay, so in a sense, forecast 2 that was sort of more bullish about England's chances came closer to the actual thing when England actually wins. Okay, so the bottom line is that the choice of the scoring rule is not innocuous, and that's about all I'm going to say about it. I think it depends what type of tournament and what type of contest you're running, and I don't know what you think is sort of a better forecast between those two. And I could think that one could maybe use an axiomatic approach and say, look, a scoring rule should satisfy these n axioms, and then try to think of a scoring rule that that satisfies all of these axioms. And I don't know if such a scoring rule exists. It could be that. I mean, of course, it depends on which axioms you want it to satisfy. I'm not a theorist, and I don't do axiomatic game theory, so I won't be able to say much more about that. Okay, so here is, I think, an interesting point. Okay, so in a contest, do forecasts elicit their true probabilities? Okay, so what do I mean by that? Suppose that forecasters have an incentive. They participate in a winner-take-all contest. Okay, so they care about being the most accurate forecaster. Should they predict? Should they issue a forecast that corresponds to their true probability? And the short answer to that is no. Okay, so example, suppose that you just have to predict one event that can either happen or not happen. Okay, and this event happens with probability P, and there are two forecasters, and they both agree that the probability that this event happens is P. But it's a winner-take-all contest, so the person that makes the most accurate forecast wins a prize, and the person who makes the less accurate forecast wins nothing. And if if the two players make the same forecast, they split the prize equally. Okay, so without less generality, assume that P is greater than 0.5. So if player 1 says the probability that the event happens is P, let's say 0.7, players 2's best response is actually any number greater than P, right? Because with probability 0.7, he will win the prize. Okay, you get a value of 1 if the event actually happens. Okay, but if you just said P equal to F1, the same forecast as player 1, then he would get just 0.5. Okay, with certainty. Okay, so 0.7 is greater than 0.5, and that is sort of the one line proof that says that player 1 is he or she should make a forecast that is greater than the true probability. And by this argument, it's actually easy to show that there is a unique Nash equilibrium in this game where both players converge to the extreme. They both say that the event will happen with certainty. Okay, so in the sort of Trump versus Clinton game between Nate Silver and Sam Wang, they both should have said, or maybe Sam Wang was playing game theory and he was saying Trump Clinton will win with probability 1, and that was indeed sort of the most likely outcome, but that perhaps was not his true probability. I think it was, but this is just sort of Okay, so I think this is interesting because you say, look, we in a sense, what does it mean to rank forecasts where these forecasters actually are not revealing what their true probabilities is? Okay, so that doesn't really tell me much. So there may be some room for optimism. So in the game described above, meaning there is a single binary event, there's a winner take all, and the prize is split equally in case of the tie. And if there are, infinitely many players, the unique Nash equilibrium is for P share of the players to predict 1. Again, this is assuming that P is greater than 1. No, actually, this is true for any value of P, sorry. And for 1 minus P players to predict 0. Okay, and this is, again, it's a the proof is a couple of lines. So this means that in this particular contest, we can actually recover the true probability by aggregating these sort of binary predictions by all of these forecasters. Now, this is a little bit of an artificial and silly example because if all of the forecasters have the same subjective probability, which for the sake of argument is also the objective probability, then why do we need a contest to figure out who has the most accurate probability? What happens if players have different subjective probabilities? Things get a little bit more complicated. But I think that in the case of a single event, it's still going to be the case that there's going to be an equilibrium where sort of some share of players predict 1 and some share of players predict 0 with certainty. Okay, so and I guess that if P is large enough, sorry, if N is large enough, you should be able to recover what the true probability or the let me just say that you're going to recover a probability which is some I'm not sure if it's the average subjective probability in the sample. I need to figure it out. Okay, so let's just leave it at that. Okay. Now consider the sort of Women World Cup example, and let's make it even simpler. Okay, so suppose I just want to the event is the pair of teams that qualifies from Group A. Okay, so there are 6 possible distinct outcomes. Either Norway and New Zealand qualify, Norway and Switzerland, Norway and the Philippines, New Zealand, Switzerland, New Zealand, Philippines, and Switzerland, Philippines. Okay, so that's 4 choose 2 possible outcomes. Now there are 8 groups like that in the World Cup. Okay, so the possible distinct outcomes in 8 World Cup groups is 1.7 million. Okay, and if I take the whole outcome of the World Cup, not just who qualifies to round 2, but all the possible outcomes, including the winners, my calculation, which I think is accurate, but it could probably not, but I don't think I'm too far off in terms of order of magnitude, there are 55 billion possible outcomes for the World Cup. Okay, so I have a conjecture that if there's a unique Nash equilibrium, is for, again, if all the probabilities are known, everybody shares the same objective probability, the unique Nash equilibrium is for exactly PJ share of the players to make the forecast that the composite outcome J happens with probability 1 and all of the other outcomes happen with probability 0. Now, this means that in a contest like the predicting the Women's World Cup, there is no unique Nash equilibrium that has this property because you don't have 55 billion players. Okay, and also the probability of winning the contest is vanishingly small if you say, look, England wins with probability 1, the United States loses in the final with probability 1, Germany and France are the losing semifinalists in probability 1, etc., etc. Okay, so that would be a not very clever prediction to make, and it's also impossible to coordinate an equilibrium. Like I mean, this is maybe a general question about how do agents coordinate on an equilibrium. It's also an issue here. So I think there are some open questions. Do players elicit true probabilities? And can one devise a contest in which the optimal strategy is to reveal the true probabilities? There may be some similarities here to auction theory. So the fact that players will converge to either outcome 1 happens with probability 1, or it doesn't happen to probabilities with probability 0. It reminds me a little bit of first price auctions, that there is something similar to the winner's curse. So maybe the mechanism to get players to elicit their true probabilities, maybe it would have some features similar to that of second price auctions or victory mechanisms or things like that. Not my area of expertise. I don't know the answers to these questions. Some people may have more to say about it. Any questions? All right. Okay, so let's look at one specific example of these probabilistic prediction contests. If you've been wondering what I do during my spare time, I have been organizing probabilistic prediction contests for various soccer tournaments, the World Cup, the European Championships, Copa America, the Women's World Cup, the European Cups, both the group stage and knockout stages, and national leagues. So what I'm going to do in this section is, first of all, I'm going to show you what a sort of one of these contests looks like, what you have to do. Then I'm going to do talk a little bit about how do you predict the outcomes of soccer matches and soccer tournaments, and then I'm going to do some comparison of different methods. Okay, so this is the spreadsheet, or part of the spreadsheet, for the Women's World Cup. Okay, so there are in this case 4 groups. These happen to be, it's actually so the top half of the draw in the Women's World Cup. Okay, so groups A, C, E, and G, all their matches play in New Zealand, and it's sort of like a mini World Cup with 16 contestants. Whoever comes out of this gets to the final and gets to play the winner of the Australia World Cup. Okay, and this is what it looks like. So this is what I call agnostic prediction. So agnostic is a contestant who believes that all teams are exactly equal in quality. So each one of the teams has a 50% probability of being eliminated in round 1, a 25% probability of being eliminated in the round of 16, 12.5% probability of being in the quarterfinals, etc., etc. Okay. Notice that there are some constraints here. So these cells where it says 2 and OK, what does that mean? Well, the number of teams, the total number of teams eliminated in round 1 from group A has to be equal exactly to 2. So the sum of these 4 cells has to be equal exactly to 2. Okay, and these 2 groups cross in the round of 16, group A and C. So the winner of group A faces the second place team of group C, and vice versa. So there have to be exactly 2 teams eliminated in the round of 16 out of these 8 teams. Okay, and then there have to be exactly 2 teams eliminated in the quarterfinals of the World Cup. So the sum of these 16 numbers has to be equal to 2. And there's going to be exactly 1 team eliminated in the semifinal. So the sum of all these numbers is going to be equal to 1. All right, and the goal of the contestants is to fill in all these cells with their best possible forecast. So how do you make a prediction? Well, I'm going to start with manual forecast. So I could go back to that spreadsheet and start filling in these names, these numbers manually. Okay. And how do you do that? Well, perhaps you have a lot of football knowledge, or inside information, or you trust the eye test, or vibes, or whatever it is that you prefer, and you start making predictions. Okay, so the pros of this, what I call human approach, is that it's relatively simple. You don't need to estimate a complicated statistical model, simulate matches, etc. Perhaps thinking of some of those strategic considerations I was talking about before, maybe this is, the human prediction is better at maximizing the probability of winning the contest. Okay, so perhaps I don't really believe that, the United States will win the World Cup with probability 1, but they are the favorites, and maybe the best way to get a good score in the contest is to say that the United States will win with probability 1. The cons of this approach is that it's not very scientific. It turns out that if you've ever tried to fill one of these matrices manually, it takes a lot of time, because getting all the constraints to be satisfied is a little bit of a pain in the head. But I would argue that it's interesting to analyze how manual predictions do relative to sort of statistical models. Can humans play as if they solve this complex optimization model? So when I'm going to compare some of the methods, I'm going to show you the results of some of these predictors. Okay, so let's say that you've learned a little bit of statistics and or machine learning or whatever. So you want to do something a little bit more sophisticated than that. So in practice, what you'll do is you're going to simulate the tournament. And how do you simulate a tournament? Well, the first thing that you have to make a probabilistic forecast for the outcome of individual matches. Okay, whereby I should say outcome and specific result. So you care about whether England beats Denmark 1-0 or 5-0. Because that's going to affect goal difference and the probability of qualifying for the next stage. And then you simulate these individual matches, and you simulate the entire tournament, et cetera, et cetera. Okay, so that's what you need to do. Okay, so let's start by the forecasting individual matches. And this is, I would say, this is an area that has received quite a lot of attention, including in the academic literature. How do you sort of model the outcome of soccer matches? I would say that very broadly, the models can be divided into 2 broad classes. One is, you say, well, we're going to try to make a forecast based on past results. Okay, so England has won a lot of matches recently. They won the European Championship last year. Probably they're a pretty good team. Haiti, maybe not so good. They lose most of the matches. And so I'm going to use those past results and nothing else, pretty much, to predict outcomes. But there are other types of forecasts. I'm going to spend a little bit talking about, betting odds, and how it can, work for this, particular, for these, tournament contests. There are forecasts based on player quality, and there are, what I'm going to call advanced metrics. Okay, so I'm going to spend a little time on those things as well. Okay, we start from the very simple, bivariate Poisson. So the number of goals scored in a soccer match is discrete, first of all, and typically it's not a very high number, so it makes sense. Why don't we model it as a Poisson random variable? And the basic Poisson model is say, let's assume that the goals scored by team I and team J are independent Poisson random variables. Okay, with parameters lambda ij and mu ij. Okay, so lambda ij is the expected number of goals scored by team I when it faces opponent J, and mu ji is the expected number of goals of team J when it faces opponent I. Notice that so these lambdas have to be positive. So as in sort of Poisson regression, the log of lambda is a linear function of, in this case is just a home field advantage factor, just a constant that reflects the fact that we think that, playing at home increases your probability of scoring, and essentially individual fixed effects for, the own team and the opponent team. And this is easy to estimate if you have access to a statistical software that runs Poisson regressions, for example, Stata. But also there are versions of Poisson regression in R, Python, etc., etc. All right, some basic issues with the Poisson model. Which previous matches should you include in the data? And how much weight should you give to more and less recent results? Okay, so if you want to predict the outcome of Manchester City versus Preston North End, you probably want to take into account that Manchester City today is a pretty strong team, and Preston North End not so much. But 100 years ago or 150 years ago, things were different. Okay, I don't even know if Manchester City at the time existed. And so you want to have some way of perhaps give more weight to more recent results. There's an issue with this independence assumption. So the Poisson model underestimates nil-nil scores and 1-1 scores and overestimates 0-1. This is just sort of an empirical regularity that has been found by many researchers. And so the most popular variant on the Poisson model is this method devised by Dixon and Coles, where they basically introduce some dependency between this, the goals scored by team 1 and team 2, and in a way that fixes the, the underestimation of sort of low scoring draws. And they also have a way to, give more weight to more recent results relative to less recent results. It can be estimated by maximum likelihood. It's very popular. The code for estimation, you can find it on, a bunch of blogs. That relatively easy to do. There are a lot of extensions and variants. This is a non-exhaustive list. I won't go too much into it. Okay. Okay. So that method was based. Okay, let's take a sample of actual matches. Let's try to calculate these individual team abilities based on their historical scoring rates, and then predict outcomes using a Poisson model. An alternative approach. Use historical match results to develop a rating of teams. Okay, and then use a Poisson or any other model that you like to estimate the scoring probability. Okay, so this somehow reduces a little bit the dimensionality of the problem, because now I'm saying, Xij is the number of goals scored by team I when it faces team J. Now it's a Poisson random variable. Again, there's depends on, home field advantage. And then this can be a sort of semi-parametric, non-parametric function of, the rating of team I and the rating of team J. Okay, so you could just put like linear terms, you can put quadratic terms, you can put the interaction of, rating I and rating J, and do all sorts of sort of, funky nonlinear stuff. So by far the most popular method is the ELO rating system. So Arpad Elo was a Hungarian mathematician who developed over, the reference is this book published in 1978, but I think the method was developed several years earlier. And he developed a method to rank chess players. Okay, so chess matches, like football matches, can typically have a winner or a loser, or they can end in a draw. And it turns out that there are publicly available ratings of men's international teams at this website, www.eloratings.net. And there are also ratings of club teams in European football, okay, at this website, clubelo.com. Okay, so you can go to those websites and get the ratings for any particular set of teams. Okay. Some of the ingredients of the ELO system, basically it works based on this. There is an updating formula. So the rating of particular team at match n+1 is equal to their old rating Rn plus an adjustment factor, which depends on these three terms. Okay, so K is an adjustment parameter. Lambda is a function of goal difference. And y minus ye is the difference between the actual outcome of the match and the expected outcome. Okay, and the expected outcome is equal to this formula. That's the formula that is used by ELO. So dr is the difference in rating between the two teams at the beginning of the match, and HFA is again a home field advantage factor. Okay, so there are some choices that one can make about the parameter K and this goal difference function. You probably want to take into account that if team A beats team B 5-0, that carries more information about the relative strength of the teams than if the match ended 1-0. Okay, so there are choices that one can make between for those two variables. Okay, turns out there's this paper by Vattum and Arntzen, and they evaluate the ELO rating for Premier League matches in the 1990s and 2000s. And their finding is that the optimal value of these parameters is K equal to 10, and the lambda function is just a sort of linear function of goal difference. Okay, so 1 plus GD. For international matches, the ELO rating system uses a variable K. So this takes into account the peculiarities of the international game, that there are, the World Cup is somewhat more important than perhaps continental championships. Sometimes teams don't send their, best representatives to continental championships. Qualifiers are maybe less important than, the final stages of the World Cup or continental championships. And then there are a lot of friendlies. And so maybe friendlies, they're used to test new players. So maybe they don't really reflect as much about the team's ability as others. Okay, so this is the parameters that are used by the ELO rating. So turns out there is no established ELO rating for international women's football, and so I tried to develop one for the 2023 Women's World Cup. I downloaded data from Kaggle. By the way, I should have said something about Kaggle, because Kaggle is a platform that runs a lot of these prediction contests. It's really about sort of, for machine learning, you should have a look, okay? Not just for football, it does it for sort of a lot of things, not just sporting events. It really is, and they're actually sort of, they have a lot of tournaments, sometimes with, pretty substantial prizes, and, teams of, engineers and computer scientists, compete to win these, prizes that sometimes, go to in the, thousands of dollars. Okay. So what I did is, I did something sort of very basic. I used the lambda formula as used in the men's game, and then I just did a very simple grid search. I mean, very, coarse grid search over values of k and the home field advantage to minimize in-sample error. What do I mean by in-sample error? So given the rating, I can estimate a bivariate Poisson model with independent results, because the Dixon-Coles is a little bit too complicated for me. And then I compare the win probability predicted by that Poisson model with the win probability assumed by the ELO model. So this YE formula. Okay. And what I found here, and this is sort of rigging the data a little bit, that k equal to 40 and home field advantage equal to 70 was what gave me the best in-sample predictions. Okay, so that's what I ended up doing, and I came up with this rating for the teams that are currently the top 5 rated women's national teams, so you can see the US started low, but more or less since the beginning of the 1990s they've always been the highest rated team, and right now there's actually a pretty substantial gap between the US and the ones that follow. So England is currently the 2nd rated team. That's sort of the, I think that's Navy. France is red. Germany is black. Spain is orange, which is a combination of yellow and red. So that's what comes out. And, I was pretty happy that these results turned out to be sensible. But then I noticed that this parameter k, and James and I have had a little bit of a conversation about this, seems to matter quite a bit. Okay, so this is just the difference between Germany and the USA over time, and the 3 lines depict 3 different choices of k. So k equal to 60, k equal to 40, and k equal to 20. And the differences can be quite big, up to about 100 points in some periods, based on these 3 methods. But the exchange of points and the predicted probability of winning based on the ELO formula are actually quite different. They're a function just of the difference in rating and not of k itself. And so that raises a little bit of a red flag. Okay, so if USA and Germany were to play a match when the difference is 200 points or 100 points, the predicted probability of USA winning would be very different in those 2 things. So that made me sort of worry a little bit, and I don't really know what the answer is, but I would have hoped that things were a little bit less, more stable than what we observe here. Through some of the period, it looks as if the ratings are very close to each other, but there are periods where these things diverge, maybe a little bit too much for my taste. All right, any questions on ELO ratings, Poisson, anything that I just said? All right. So how, what
Daniel,
other, yeah.
I will ask you one question, actually. I can see Stefan's not here because he's apparently walking somewhere in Scotland. But one of the discussions I've had with him about ELO ratings is the fact that teams of chess players die, and so they leave. Their rating disappears. But certainly national teams and lots of football the clubs as well, they don't die, they carry on, and so there's arguably some kind of inflation that appears in the ratings, and you've got the US one steadily going upwards and increasing over time. I don't know if you've thought at all about that potential for the ratings being inflated. I don't know whether that ties back in with your concern about the difference versus perhaps the actual absolute levels of the ELO ratings.
I have not thought about it, and that could be a possibility. I think that one who should go back and read the original ELO book, which can actually find it online, like a PDF is there. My understanding, which may be incorrect, that there's a claim that these ratings will eventually converge, but maybe that does depend on this sort of the fact that chess players eventually disappear. Now, soccer teams, first of all, some soccer teams do disappear. Maybe not at the same rate as chess players. Certainly, teams have cycles, and at one point they were very strong, and now they are much less so. Example, Preston North End. I don't have a good sense of how these things matter. It could very well be that the non-disappearance of teams leads to this sort of constant inflation, even though my understanding is that at some point these things should sort of converge to the whatever the true rating is. That's about all I can say. Okay. So how else can you make prediction for individual matches? One very popular method is to use betting markets. Okay, and we are economists, and perhaps we believe in the efficient market hypothesis. And in the context of betting markets, it says that the betting market odds, whether you're talking about bookmakers or betting exchanges, should reflect the true probabilities of the events, or perhaps the true subjective probability of the events, after you remove the bookmaker's margin. Okay, and if you have a betting exchange with free entry and no margins, then you don't even have to worry about that. Now, when does the efficient market hypothesis hold? And again, I'm not a finance person, but my sense from my undergraduate classes that you need to have high liquidity, no transaction costs, free entry on both sides of the market. And I would argue that for sufficiently high profile matches, and one can sort of debate what high profile means, the betting volume on the 1x2, so win, draw, loss outcome, is quite large. There are a lot of bookmakers that will offer you odds on Manchester City versus Manchester United, or Barcelona versus Real Madrid, or even Barcelona versus Almeria in the Spanish league. And I think that the efficient market hypothesis is quite reasonable. But for markets, and this is not crazy, okay, what is the probability that Canada will be eliminated in the round of 16? Things are, I would argue, a lot less liquid. And so it's not obvious that these betting markets for individual matches can help you much in these tournament long prediction contests. Okay, maybe there's enough liquidity in the who will win the World Cup, but it's not clear that there's enough liquidity and these other conditions for these intermediate outcomes. There's also a question, how can you convert 1x2 odds into the probabilities of specific results? I think, I've never tried it, but I think that in theory, one could use a parametric assumption, for example, bivariate independent Poisson, and method of moments to identify the parameters. Okay, so for a specific match, say that you need to identify, two parameters, the probability of scoring of, the Poisson parameter of team 1, the Poisson parameter of team 2. If you have access to the, predicted probabilities of team 1 winning, a draw, and team 2 winning, those, you only have like, 2 independent probabilities there, 2 independent moments, but there are 2 moments, 2 unknown parameters. It sounds like it could be possible to identify those 2 scoring parameters. I have no idea whether this works well in practice, but I think that this could be an interesting, maybe some people have done it. Okay, other prediction methods. Number 2, you may think that the outcome of a football match depends on, the player quality. Okay, so you may have noticed that, Inter Miami in MLS was, bottom of the table, the worst team in MLS, and then they scouted a couple of young prospects, Lionel Messi and Sergi Busquets, and suddenly they're winning all their matches. There are a bunch of sources where you can get, coarse or maybe not so coarse measures of players' ability. Okay, so Transfer Market is a crowdsourcing website where, experts or fans or, whoever it is that, is a member in Transfer Market, assesses the market value of individual players. Okay, and there's actually a paper by Peters, who actually may be part of this group, that evaluates the predictions based on transfer market values in terms of predicting match outcomes.
Daniele, but I don't see him here now.
Okay, well, hi, I forgot your first name, but
Thomas.
Hi, Thomas, if you're here. There is now publicly available data on player wages, at least for the top 5 leagues. Somewhat accurate. One can get it from this website, fbref.com. Video games, such as FIFA, or now called EA Sports FC, or Football Manager, they put a lot of resources into coming up with evaluation of player skills. Okay, and I've seen these used in actually economics papers, and I think including papers that we have seen in this, in this, in this workshop so far. Okay, and fantasy football platforms as well, right? There are players that are given values based on fantasy football. Okay, so you could calculate the team rating as a function of the quality of its players. So you can take the average, transfer market value. Maybe you want to take the average of the log of the transfer market value, so it's a geometric average rather than an arithmetic average. And you can look at a lot of things like, okay, what really matters for the outcome of a contest? Is it, the weakest link, the strongest link? Does it really matter to have a, very good midfielders or very good goalkeepers? And so let me show you something that, this is the 2022 World Cup, and the outcome of some of these, player-based methods based on transfer market values. So the first 2 lines, so again, here everything is multiplied by minus. So the log score is multiplied by -1. So lower values mean better predictions. The bottom line here is random guessing or agnostic. That's sort of a benchmark. Transfer market is just sort of the, this is the geometric mean of transfer market values. Transfer market adjusted makes an adjustment for player age and player position, reflecting the fact that sort of, there is a kind of a Mincer equation type of relationship between transfer market value and player age. It's sort of, inverse U-shaped. And forwards are rated more than midfielders and defenders and goalkeepers. So they do a little bit better than random guessing, but I was sort of mostly interested in some of these things. So the weakest link, so I looked took the the World Cup rosters and look at the I think it was the 5 weakest players, so the players with the 5 lowest transfer market values. The middle link is the people in the middle, and the strongest link is the middle and the top. And you get this result that I think that is interesting, that weakest link tend to do a bit better than middle link and strongest link. And I think this could be interesting, perhaps. This is you should view this as a relatively small sample. Okay, so not it's just like one tournament. One could look at sort of individual matches and see how they did. Okay, in terms of what positions really matter, goalkeepers and defenders seem to be more important than midfielders, and forwards, they are almost as bad as random guessing. Okay, which I thought this was interesting and perhaps new, and perhaps also a little bit in contrast with conventional wisdom, where the heart of a team is a midfield. You really have to high quality midfielders, and that didn't quite turn out to be the case in this particular contest. Until what time do we have?
You've still got we've just gone 3:30, so we've got about another half an hour or so if we want to take it.
Okay. All right. So other method number 3, advanced metrics. So some of you may be familiar with this, some of you perhaps not. So soccer is a low-scoring game, and often the final score depends on a lot of random factors. And in recent years, people have developed new advanced metrics that supposedly capture better what happened in a match. Okay, so the number of goals is a very imperfect measure of the team's skills. So people said, well, perhaps we should look at the number of shots or the number of shots on target. But by far the most the metric that has been really gained a lot in popularity in the last few years is this thing called expected goals, or XG. And it basically says how likely is an average player to score a given shot. Okay, conditional on the distance of the goal and the angle to the goal. Sometimes these measures also include the position of the defender. Sometimes they include other parameters, whether it was a header, a shot with your feet, with other body parts, whether it came from a cross or a pullback or a through ball, etc., etc. And what this measure is supposed to capture is what casual observer typically, how a casual observer typically reacts to watching soccer matches. That was a sitter. I should have scored it. Okay, that would be a shot that had a high expected goal, or XG value. Or that was a bit of a hopeful effort. You took a shot from 35 yards out. Goes wide by a large margin. You don't really hope that you would score from that. That is a shot with a low XG value. And it turns out that XG has been found to be more predictive of future outcomes relative to past goals, shots on target, and other measures. How people have done this, they typically look at the cumulative XG difference, so difference XG4 minus XG against, in the first M matches of the season, and then see how that does in predicting total points or goals scored and goals conceded from match M+1 onwards. And it turns out that XG did better than goal difference or shot difference and other measures, especially in early parts of the season. Okay, a lot of this was based on work by amateur analysts on Twitter and on blogs. It turns out that soccer clubs realized that they should develop their analytics department, and they hired a lot of these people, and now they're doing all of their interesting research behind not in the public domain. So I'd be curious to see whether some of these initial results on the predictive measure quality of XG based on when these models were developed, which was around 2013 to 2016, whether they still hold or perhaps they even improve, given that XG models have improved over time. So you could ask how would a model based on XG do in terms of predicting match outcomes. 538 soccer predictions, I'm going to talk about in a little bit, did incorporate XG. It's a hybrid of a lot of these different things that I talked about. But the predictions are likely only as good as the quality of the underlying XG model. And so if your XG model is not very good, probably your predictions are not going to be very good either. And you need a lot of data to sort of calculate XG accurately. Okay, I'm going to talk a little bit about how these prediction contests look in practice. One small note, how do you go from match predictions to tournament predictions? So first of all, betting odds for individual matches are not available far away in the future. So that's a problem. You can't really just based on betting odds, which some people think are the most accurate method. The other thing you have to worry about is that team quality is not necessarily constant throughout the tournament. There are swings in form, there are injuries, the manager is fired, you bring in new players, a lot of things happen. And also sometimes, over the course of a season, a team's focus can change. So teams are on the beach towards the end of the season, they have nothing to play for. Whereas some others are desperately fighting for survival, staying in the Premier League or whatever, or some other teams may concentrate on domestic and continental cups, and these are things that are difficult to forecast ex ante. So a possible solution. So suppose that you have some rating like the ELO rating, you could say, well, I'm going to add some AR1 noise to the ELO rating and base my predictions for what's going to happen in April and May based on this AR1 process. This is something that I have seen done. I find it kind of weird. It's called running the simulations hot. This means that you adjust the rating of teams after each simulated match, okay? Which to me seems kind of weird, but it's another way of accounting for this, future variability of ratings. And again, I don't have a good sense. I don't know if people have done, comparisons of sort of one method versus the other. Okay, so let's see. How do we compare different methods? So I'm going to compare performance in the prediction contest that I run for just for the European Cups, and I have separate contests for the group stage and the knockout rounds. I'm going to pull everything together. I could do some of the analysis separately, but I didn't have time to show it to you. And I'm going to do it from 2016, 2017 onwards for a total of 28 contests. The reason I selected this sample, even I have data for further back, is that that's when 538 started to use its, publish its predictions, and so I wanted to have that as a benchmark. Okay, so I'm going to report the results of a selected participants. Each one participated in at least 20 of these 28 contests. So the club ELO-based predictions, which are exclusively based on past results. Transfer market, so the geometric mean of transfer market values. That is just a prediction based on player quality. 538 is a hybrid based on results, on player quality, on expected goals. I have 5 human experts. One of them is myself, but I'm going to keep the names anonymized, so because I don't want to brag or embarrass myself. And then I have agnostic, who basically just makes random predictions. And then I'm going to report the outcome of collective consciousness, which is the average of all predictions in a contest. Okay, so this is everybody including the people above, but including everybody else who participated in one of these contests. For example, no, actually, I think James never participated in one of the European Cups contests, so you wouldn't be there. But that's the idea of collective.
Not yet. Next season.
Next season. All right. Okay. So this is the outcome. This is the table. So this is just the number of times out of these 28 contests that each one of these prediction models came out of top. So 538 won 4 times. Transfer Market won 4 times. Club ELO won 3. But notice that these human experts, with the exception of expert 1, all won at least once. And the total number of wins of these human experts is I think almost as large as that of the sort of the model-based predictions. And I think this has to do with the fact that humans will tend to take more risks in a way that sort of increases their probability of winning the contest, based on some of the discussion that I had earlier. Okay, this is just the number of top 3 places. So 538 does pretty well. The entries here are ranked by the average percentile rank. So if you came up first, you get a score of 100. If you came up last, you get a score of 0. So 538 did best. Collective consciousness did just very slightly worse. Notice that collective consciousness never won. Okay, so here I think this is not entirely surprising. If you want to beat the bookmakers, you have to deviate a little bit from the crowd. You have to take some sort of gambles, and collective consciousness aggregates all of the predictions. It never really comes out on top. Okay, and this is just sort of more of a quantitative measure of how these methods scored relative to agnostic and relative to collective consciousness. So the way, I should have said, this is everything here is based on the log score, which is what I actually use to rank these contests. I could calculate the Breyer score, but I haven't done it here. And if you exponentiate the log score, you basically get the interpretation of the log score is what is the predicted probability that you assigned to the events that actually happened. Okay, so the score relative to agnostic is how much better in percentage points was your prediction relative to agnostic's prediction. And here it actually turns out that very slightly collective consciousness comes out better than 538, but we're talking about third decimal point, and Club ELO also comes very close. Now I think this is especially interesting for when I look at the the experts. Some contests are easier to predict than others, okay, because the favorites do better. Okay, so so a useful benchmark is how do you do relative to collective consciousness, and nobody beats collective consciousness in terms of average score. So you need that. You see that collective consciousness has a value of 0. Everybody is has negative values. They do a little bit worse relative to collective consciousness. And again, here actually you find that the same thing. So Club ELO and 538 are very close in terms of their score relative to collective consciousness. Okay, so couple more things. So here are some fun things. So this is predicting the Women's World Cup. This is perhaps very small. I have here 4 predictions. One based on the ELO rating, one based on the FIFA rating, which is a quasi-ELO rating, but that's what FIFA's official rating system is. And on the left, sorry, so these are groups A to D. These are groups E to H. That's just the probability of qualifying to the second round. let me actually show the next figure, which is the probability of winning the World Cup. Okay, and based on my method, I found the US to be huge favorites. They had actually a 59% probability of winning the whole World Cup, which is a lot higher than all of these other methods and also a lot higher than the bookies. So if I really believed in my method, I would, run and, put a, well, I said I wouldn't endorse gambling, so I'm not going to endorse gambling. There's also this yellow bar, which I'm going to talk about in a second. This is called econ, or econ 0. And what is econ 0? Okay, so this is what I call the economic model. So suppose that you didn't know absolutely anything about soccer. Okay, you have no idea who the good players are and who the good teams are, but perhaps you can come up with a theory that maybe success in soccer is a function of population, that you have a bigger talent pool to draw from. Perhaps it's a function of GDP per capita. Why? Because, maybe you have healthier athletes, maybe you can invest more in infrastructure, maybe you can pay for better coaches. So GDP per capita should matter. If you're thinking about, the women's game, you may think that, soccer success depends on, some measure of gender equality. Is it surprising that, Scandinavian teams have tended to do quite well in the women's game, more than sort of Southern European teams? And, somebody may tell you, look, some countries are crazy for soccer and some countries not so much. And so perhaps you want to measure how sort of soccer crazy a country is, and you can maybe proxy that using continent dummies. And it turns out that this economic model doesn't do terribly badly, okay? Even if you know absolutely nothing about soccer, it tends to beat random guessing, and it usually ends up in the middle of the pack. So it hasn't, won any of the contests, but it's not too bad. I wanted to show you some of the, regressions that I used to, calculate these economic predictions, but I didn't have time to do that. So I'll stop here.
Great, thank you.
These are the selected references.
Perfect. Thank you, Daniele. We've got some time for some questions if anyone has any questions from the audience. And Louis.
Do you hear me?
Yep.
Thanks, Daniele, for a very comprehensive and very clear presentation. I enjoy it very much. I have a couple of questions. I will probably restrict myself to 2 questions. The first, what is your advice in terms of estimating different sets of parameters depending on the stage of the competition, for instance, or things like that? Because you are tempted to use different sets, but you reduce the size of the samples. So what is the balance? For instance, in this kind of tournament, you have a group stage and the knockout stage. Do you estimate different sets of parameters for these 2 stages?
Did you have another question? Should I answer them both together, or should I answer this one?
Okay, the second question is a question I asking myself for a long time. Do you have any idea to improve the prediction of getting a draw?
Okay, so the way that I estimated, but I should say I'm an amateur on this, okay? And people have spent a lot more time thinking really hard about some of these issues than I have. So I'll, preempt that by saying that. The way in practice that I, calculate these estimations, I actually, for the Women's World Cup, for the Women's International ratings, I gave exactly the same weight to all matches. Okay, so the updating parameter, I gave exactly the same weight to a friendly or to the World Cup final. I actually think that in the context of the women's game, that is not too bad of an assumption, because maybe with the exception of the last few years, when the club's game has actually started to emerge and has become sort of pretty serious, the international game was really the only way that women had to to show their quality, right? So a friendly between the US and Canada was taken very seriously. It's not that club teams didn't release players from for the friendly, or somebody just had an injury, couldn't show up for international duty. And so I'm just treating all of the matches in the same way. My sense is, as you say, you could try to give sort of more weight to matches played in the final stages of the tournament relative to the group stage and relative to the qualifiers. But you do end up with a problem that you have fewer matches. There is something that I should mention here, which is that knockout matches sometimes go to extra time.
Yeah.
And I am pretty sure that the way that I have done these estimations, I have not taken into account extra time, which I think is wrong. So, a match that lasts 120 minutes is not the same as one that lasts 90 minutes. And I think in this particular implementation, I also didn't really take into account extra time in generating the predictions. So essentially, I'm assuming the goal scoring probability, if the match lasts 90 minutes, or 90 minutes plus injury time, without taking into account that if it's a draw at the end of the 90 minutes, then they're going to play 30 more minutes. That is relatively easy to implement. I did not do it in this particular implementation, but I think it should be done. Yeah, I think that answers the first question to the best of my ability. The second question about adjusting the probability of draws, everything here I did not make any adjustments. So these specific predictions, I estimated a simple independent bivariate Poisson. I did not use some of these, Dixon calls or other methods that, kind of inflate a little bit, draws on the probability of draws. But there are methods out there. I think that so that's another one that used something slightly different from the Dixon Coles method. Okay. Papers, I think, those are the ones that I know of. But this literature is very rich, and as I said, I learned some of it, only in the last couple of weeks. So I imagine that some of you probably know a lot more than I do here. And I'm welcome if anybody does know and wants to sort of jump in, please feel free.
Thanks very much.
John-Louis is perhaps being modest. He has a talk from the Roses series on precisely the effect of extra time on probabilities of match outcomes. So that's on YouTube if you want to.
Okay.
I don't know if that's become a paper since your presentation.
Sorry.
I wondered if the presentation you gave on, adjusting for
no.
Yeah. Thank you, Jean-Louis. We've got probably time for one more question if anyone would like to raise their hand and ask a question. Well, what I will do, Daniele, is just check a couple of notes that I made. One was that you referenced Raftery as one of your people on the proper scoring rules, because he's done work on model averaging and forecast combination, which essentially is what your collective consciousness is for your competition. And I guess as you found, it kind of stands to reason that the average wouldn't win, but it would do fairly well, because I guess it can't win because there's always going to be a forecast that's better than it's averaging, and it's weighed down by the worst forecasts. I also, I like your economic model as well. I had a PhD student a few years ago. Well, I shouldn't say a few years ago. She did the work a few years ago, but she just successfully defended. Who did a kind of a similar thing to you, but for men's football, kind of GDP thrown in there to try and explain outcomes and so on. And I wonder, I think it's just kind of casual thinking, but my sense is that, as you say, a lot of those kinds of measures work well for the women's game, but probably not for the men's game, because Argentina go and win the World Cup, and they score badly on all these kinds of measures, and Italy win the European Championships and score badly on a lot of these measures. And
they're both pretty big countries.
Yeah.
So I think that the difference between the continent dummies or the confederation dummies, they explain more and they improve the prediction in the men's game more than they do in the women's game. In the women's game, GDP and population do pretty well. By the way, so there's even in the men's game, so if you rank countries by GDP per capita and population, not surprising, the number one country would be the United States, which happens to be the best performing team in the women's game. They are not too bad in the men's game, so people may not realize, but US is consistently ranked somewhere between 10 and 20 in the men's game, which is not the very top, but it's not too bad either. Since 1998, the US has advanced farther than Italy in the World Cup in every single World Cup but one, which is the one that Italy won. So traditional soccer powerhouse versus upstart nation that can't even call the game with its proper name. So you have to be a little bit careful. The U.S. does a lot better than Martinique and Guadeloupe and some of the other small, not very rich countries that it plays against. But I think that, I don't remember exactly. I think that the model with the continental dummies in the men's game explains. I think you get an R-square of about 0.7, maybe. Maybe I'm exaggerating. That's probably too much. So actually, I have it right now for the women's game. So the simple model without the consonant dummies has an R-square of 0.65. Just three variables: population, log GDP per capita, and the gender equality index, which actually does almost nothing. It's just barely marginally significant.
Interesting. Fantastic. Well, we've hit 4 o'clock, so we'll wrap up. So thank you very much, Daniele, for a hastily organised but fantastically interesting talk on a lot of work that you've been doing, fascinating work over many years. Let me check the schedule. I think we don't have. No, we do. We have a talk next week on August 4th, Felix Rüssel from Braunschweig in Germany, presenting sports clubs and populism, quasi-experimental evidence from German cities. So potentially quite topical again. But thanks, everyone. Good to see everyone. Thank you, Daniele, and do have a great weekend.
All right. Thank you very much for all the comments and questions and for having me here.
You're very welcome, Daniele. Thank you very much.